Okay, let's talk a bit about sensor uncertainty, why it's an important topic in vehicle applications, and also how we can try to minimize its effects. So basically, in order to establish any type of accurate control, you need accurate sensor information, because you need to know the state of the object that you are controlling. So in our case, we need to get accurate sensor information from the vehicle out there on the road, which is a difficult task because the road is quite a chaotic environment. So this is no laboratory or factory floor. All of our sensor information is heavily flawed. If we think about our sensors, for example, if we have a camera, we are pretty much distracted by rain, snow, fog, all types of bad lighting conditions, like the sun being low there on the horizon. If you have a LiDAR, it's pretty much the same problems, except the lighting problems. If you have wheel encoders, the wheels are slipping, the information is unreliable. If we're using an inertial measurement unit, there are all kinds of bumps on the road and so on, which cause, again, flaws in that information. So yeah, if we really want to control our vehicle, how can we reach that accurate sensor information? Because it is quite a fine process. Like if we want to keep the vehicle on the road, we need to know its position accurately, so we can control it. And let's say that we are measuring the position of the vehicle with a GPS, and now in very favorable conditions, a regular standalone GPS has an error of approximately 2 meters, or that is the range that the error is most likely. This is assuming clear visibility of satellites, so there are no tall buildings, urban canyons, anything like this. So we are getting good GPS data, and even though it is good GPS data, it is still far from being sufficient for actually knowing the location of the vehicle. If we look at here, the blue circle kind of visualizes where the vehicle could actually be if we have gotten a single position measurement from the center of the circle. And yeah, so basically the vehicle, it could in reality, it could be here, it could be here, or it could be somewhere else. So you understand that it is a difficult task to control this vehicle and keep it there on its lane. So how do we overcome this issue? Well, to that, there are multiple filtering techniques, and the goal of the filtering is to basically reduce the noise in the data and to get more reliable sensor information, removing the noise from the data. And yeah, here we're gonna talk about probably the most famous filter, the Kalman filter, which is very widely used, and more often when people explain this filter, they try to go through all the details, try to get the complete picture with every detail. But I'm gonna try to simplify it a lot, so we can get to the bottom of it in this kind of limited time that we have to spend on this topic. So basically, I'll be cutting a lot of corners. I'll be introducing only the important parts that matter here when we're talking about basically positioning the vehicle, and just trying to get the main idea across and show an example of how to build a Kalman filter for this application. But yeah, there's gonna be I'm gonna cut some corners, and some things are gonna be simplified. But yeah, let's look at this this example for a bit. So if we have a vehicle here, and we've gotten a previous estimate from it, from our localization system, and that is marked in red. And we also, based on the data, we have seen that the vehicle is traveling 100 kilometers an hour. So let's see how believable is this sensor reading that we are getting next. And this is there in blue. So that is the GPS reading that we have got after the previous estimate of the vehicle position. and the time between these measurements is 0.1 seconds. Okay, so let's think about this for just a couple of seconds. Is this a good GPS reading, or has there been noise affecting this reading? So we know that the vehicle was traveling 100 kilometers an hour. So to me it seems quite unlikely that the GPS reading would be there behind the vehicle. And we can try to make this a bit more quantitative by the simple calculation. So basically, using these elementary physics equations, we can see that the time traveled should be the speed times the time spent. I mean, the distance traveled should be the speed times the time spent. So we can see that this is a little bit under 3 meters that the vehicle should have gone forward. So based on this information, we can say quite reliably that okay, there has probably been something wrong with the sensor. We shouldn't trust this measurement information that much. And well, this kind of example I gave, Kalman filter actually operates quite closely to what we talked about here, very simplified but still. So basically, we have the estimate from our model, which in this case was just the speed times the difference in time, and then we have the measurement, and the information from our model is called prediction, and the information from our measurement is called the update. And the Kalman filter will give us a position estimate that is kind of somewhere there between. So it is actually, it's a lot more complicated, but this is kind of what it's doing in a simplified manner. So in reality, it's doing kind of optimal weighted least squares with probabilistics behind it, basically weighing the different data. But anyway, this is what it does. It takes the prediction, it takes the measurement update, and then it combines the kind of best estimate for the system, the vehicle. And then the Kalman filter basically loops these continuously. So always prediction, update. So it's combining data from the model, the prediction, and then the measurement update. Okay, so let's jump into it in a little bit more practical way. So let's look at this problem of tracking the position of the vehicle with GPS and how we can do this. Yeah, so let's go back to the nice image we have, and first we're gonna build our vehicle model so we can perform the prediction step. And we're gonna model our vehicle with the state that is shown here. So this vector is vehicle state. We have x and y coordinates, and then we have the derivatives of those coordinates. So basically the velocity in x direction, velocity in y direction. Nothing more complicated than that. A very simple model. And yeah, so this is the kind of model we have that kind of gives us the state. So we can see that the state at the time step k is basically a very simple equation from the previous state at time step k minus 1. And if these matrix calculations are giving you any trouble, feel free to always kind of get them to these scalar equations. It's the exact same thing. The matrix vector representation is just a lot more convenient in many cases. But anyway, we can see that the model is really nothing too special here. All we are saying is that our next x coordinate is the last x coordinate plus the speed times the difference in time, and the same for the y coordinate. And we are saying that the speed in the velocity in the x direction at time step k is the same as it was at time step k minus 1. And for velocity in y direction, the same thing. So velocity in the y direction is the same at time step k as it was time step k minus 1. Okay, yeah. So let's go back to the matrix representation. So this is our vehicle model, but it's still lacking a little bit. So it cannot be exactly like this. If we think about it a bit, we were saying that the velocity in both x and y direction, they stay the same, and that is probably not a very good model. That is quite rigid. There is no flexibility in it, because, well, naturally the car accelerates as well, so the speed is in fact changing. So our model is not very accurate this way, and there is of course all types of other noise in it as well. So let's try to model all these noises, most specifically the accelerations that are happening with the car, by just putting this vector q here. And what the q is, it's the process noise, and that is from a zero mean multivariate normal distribution. Now, if you haven't done any probability calculations in a while, this notation might seem a bit weird, but all we are saying here is that the q is a random vector we are drawing from a multivariate normal distribution, and it is our process noise. And well, if you are not that familiar with multivariate normal distributions, Gaussian multivariate distributions, this vector on the left, that is the mean, and on the right, this matrix, this is the covariance. So on the diagonal, we have the variance of each variable, and then the other sections in the matrix denote the covariance. But we are now making the assumption that all the variables in our state are independent of one another, and they all have this variance in them. This is basically just a random assumption we are making here. Defining this process noise, it's kind of a field of its own. So there are ways to make more accurate assumptions, but we are making a kind of very uninformative assumption, just assuming that there is a little bit of variance in each variable. And yeah, so this is a four-dimensional multivariate normal distribution. Everyone is probably more familiar with the one-dimensional one shown here on the bottom left, and then there is a 2D normal distribution shown on the bottom right. And of course, getting to higher dimensions, it's not so easy to visualize, so we just have to imagine what the four-dimensional multivariate normal distribution is like. But anyway, the process noise is just there to add a little bit of noise in our model to each of the state variables. Yeah. So now this is our complete vehicle model for the system. So basically, very simple equations, just that the positions change according to velocity. The velocity stays the same, and then we add a little bit of noise there to basically show that the model is not exact. Yeah, and now if you look at our model, and we basically say that the matrix on the left, we call that A, and then the covariance matrix of the noise Q, we call that capital Q. We can go into that's basically everything we need from our model to perform the prediction step. Yeah, so as a reminder of kind of what were the steps and what was required for the Kalman filter, let's look at this slide that we saw previously one more time. So we have to remember that in red we had the previous estimate of the vehicle state. There in green we have the prediction, so what the model was saying. In blue we have the measurement coming from the GPS, and in this cyan color we have the Kalman filter estimate. Okay, so now how do we get the prediction? Well, the color codes are there to kind of help you see how it goes, But we don't have to go into the actual mathematics of the prediction. It is a bunch of matrix multiplications, but you can just think of it as a black box. It's something that software libraries typically implement. So you just have to figure out the inputs and outputs. And in this case, if we look at the kind of pseudo function predict, the inputs are the previous estimate of the state. So the m at time step k minus 1 and p at time step k minus 1. And what the m and p are, they are the mean of the estimate. The m is the mean of the estimate, and p is the covariance of the estimate. And what the estimate is, well, it's a probabilistic representation of the vehicle state. If you remember, the vehicle state was the x and y coordinates, and then the velocities in the x and y directions. The estimate is the mean, which is basically the best guess we have for it, and the p is the covariance, kind of showing how much variance there is in the estimate, how reliable the estimate is. And these are what we are constantly updating throughout these steps. But okay, we take the previous estimate, m and p time step k minus 1, and then we also take the matrices A and Q we defined previously, just constant matrices. And yeah, when we use this predict function, again, just a couple of matrix multiplications, you can think of it as a black box. As an output, we get the estimate from the prediction step, so the mean and covariance. And yeah, that's what we get from our model. That's what we get from our model, the prediction. And yeah, then we should move to the next step of the Kalman filter, the measurement update. And for that, we have to make a measurement model. And what the model is well, from the GPS, we are just getting x and y coordinates. We are moving in this two-dimensional space, so we just get an x and y coordinate from the GPS. But okay, we need to make a model that links that to the state space of the vehicle. And that is simply done by you using this simple matrix representation. So yeah, we're just saying that the x measured from the GPS is the same as the vehicle state x, and the same for the y coordinate. But again, because the measurement is not exact, we cannot define it this way, because there is actually noise in the measurement. But yeah, if the matrix representation was again causing any troubles, you can just open it like this. But yeah, to add the noise, we do it similarly as in the vehicle model, and so we just add this random vector r in our model. And r is again a multivariate normal distribution, this time two-dimensional, however, so it's a bit easier to understand. But yeah, again, zero mean was there on the left, and on the right we have the covariance matrix. Again, we are just making it a diagonal matrix, basically telling that we're just putting some variance there, and they are not correlated in any way. And what this noise just represents is that the measurements we get from the GPS, they are not exactly the same as the vehicle state. There is some noise in them, some white noise Gaussian zero mean. And yeah, again, let's denote some things here so we can use them more conveniently. We call the measurement with zk, so that the measurement at time step k. This matrix on the left, we call that capital H, which basically represents the link between the state space and the measurement. And on the right, we call this measurement noise covariance as capital R. Okay, and then how do we perform the update step? In a kind of similar representation as with the prediction step. Again, the update step is just a bunch of matrix multiplication, we can think of it as a black box, something that libraries typically implement for you, so you don't have to worry about it. But okay, if we look at what's going inside the update, it's basically the mean and covariance of the vehicle state estimate that we got from the prediction step. And in addition to this, we are also putting in there our this measurement matrix H, this measurement noise covariance R, and this measurement Z. So what we got from the GPS at time step K. And what we are getting out is the final Kalman filter estimate, so the mean and the covariance of the state of the vehicle. And yeah, again, the M, the mean, that is just a vector of 4, that is for each of the variables x, y, velocity in x direction, velocity in y direction. We get the mean estimate, which is sort of the best estimate we have, and we also get the covariance p, 4 times 4, which denotes how unreliable we think that the final estimate is. And yeah, so basically just after performing this update step, if you take the mean estimate mk, that is kind of the best guess that the filter gives you of what is the real position of the vehicle, the real state of the vehicle. And yeah, as a reminder, the Kalman filter then is just basically looping this infinitely, always. Prediction, update. You're always in the prediction step, you're using the vehicle model that you have, and in the update step, you are taking the measurement, and yeah, you combine these to get the best estimate you can for the vehicle state. Okay, yeah, so that was Kalman filter, kind of in a very simplified terms, as well as a practical example on its usage. Let's go through some final notes. Just kind of a bit more background of what was going on. Okay, so Kalman filter, the kind of original Kalman filter cannot be used in all cases. So an assumption that we are making here is that the system that we model, it has to be linear. So basically, there are no multiplications between the system variables. So we can make these models in such a way that it's always this like model matrix times the system variables, and the system variables are never multiplied by one another. So yeah, the equations have to be linear. Yeah, another big assumption is that the noises have to be zero mean Gaussians, these zero mean multivariate normal distributions. Yeah, that is the kind of assumption that all the noises can be modeled like this, and yeah, this assumption might break if there is some very heavy outliers in the measurements, some heavy noise that cannot be modeled like this. Yeah, but that was basically the limitations, a bit on the limitations of Kalman filter. There are a lot of work that continue on Kalman filter. Kalman filter as its own is like the basic solution. Then you have other solutions such as extended Kalman filter, uncentered Kalman filter, particle filters, and so on. But yeah, more about Kalman filter. If you, in the example I was talking about, we only use GPS measurements, but Kalman filter also inherently supports sensor fusion. It is an excellent tool for sensor fusion and widely applied. So, for example, in doing this vehicle tracking, vehicle positioning, in addition to the GPS, we could have used data from an inertial measurement unit, get the accelerations and so on, or we could have used wheel odometry, basically getting the velocity of the vehicle from those. And yeah, how you basically how you use Kalman filter for sensor fusion. Well, if we were using this vehicle odometry, it would be quite simple, just basically extending our measurement model. So basically the matrix capital H, we just increase that so that it's 4 times 4 diagonal, so that the model is also taking into account the wheel odometry, and then we also need to update our this measurement noise. You can see that here it's provided as a 4 times 4 4-dimensional multivariate normal distribution, 0 mean, and then 4 times 4 covariance matrix. And that is all that would need to be done to update the example I just showed you, to also include odometry data. So nothing more complicated than that. And yeah, then also the Kalman filter can be used if you have kind of redundant measurement data. Let's say you are measuring something with, you have 2 different sensors that measure the same thing. Like let's say you have 2 GPS receivers, so you're getting always 2 readings from the GPS for the location. Then there are multiple strategies to fuse that information, but a common one is to basically run the update step of the Kalman filter twice, so individually for the different readings. So always having a single prediction step and then 2 update steps instead of 1. But yeah, that is just one strategy. Okay, yeah, and I'd like to end by again highlighting that what I presented here was really a kind of simplified representation of the Kalman filter, and there is a lot more to it. If you want to really get into it and start using it, finding out more about it, where it's good, where it's not so good, what can be done with it. There's a lot more information available out there in Aalto. We have these great courses that I have listed out here. They provide you excellent knowledge of the Kalman filter, as well as other more advanced filters, like I was mentioning earlier, extended Kalman filter, uncentered Kalman filter, different particle filters, and so on. This filtering is a huge field of technology of its own. So this was like a really light touch, just to get you familiar with the basic ideas, as well as give you the capabilities of using a simple Kalman filter. Okay, yeah, that's it. Thank you for watching this video.